Hello and welcome to this video. In this video I would like to show how to calculate the risk of a portfolio of stocks. For this video I planned the following. The first thing that I would like to discuss is if historical returns are really a good basis for portfolio management. And that is important because we now switch to a different notation in our calculus. Then I'm going to calculate the risk of a two-asset portfolio. This is how it typically starts, and you might understand it a lot better if we start with a simple portfolio. Then I would like to show in Microsoft Excel how correlation influences the portfolio risk. And I would like to switch to matrix calculus and calculate the risk of a multi-asset portfolio. We're going to do that in Microsoft Excel too. Well, are historical returns a good basis for portfolio management? Of course not, because there is absolutely no chance that we simply can forecast a trend in stock prices. So, a stock that has performed well during the last years does not necessarily perform well during the next years. So there is no evidence at all in science that we can do that we can simply follow the trend. If you want to test this hypothesis, you might simply use an autoregressive model just like the ARIMA model and test whether old prices or old returns, historical returns, give any information about future returns. They don't. So you can't rely on what you measure in historical data. Accordingly, for portfolio management, we must rethink returns, and we have to go over to expected returns. And mathematically, we denote expected returns with mu. So mu as with the index as is the expected return of stock as. And this is what portfolio management is mainly based upon. We cannot measure mu as by historical data. Although I would sometimes do this during this course, just to show and just to have some numbers, nevertheless, I would never rely on that. Alright, but we want to calculate the risk of a two-asset portfolio. So, here I just wrote down the textbook formula. So the textbook formula says that the variance of a portfolio of two assets is given by the weight, denoted by omega, weight 1 squared times the variance, that's why it's squared here, so the variance of the return of stock 1 plus the weight of stock 2, also squared, they're all squared here, right? Times the variance of stock 2 and plus 2 times the weight of 1, the weight of 2, and the covariance. I just write down that this is the covariance. And this is, of course, the variance. Well, since the covariance and the correlation coefficient are two very similar approaches, we can write down the correlation coefficient between stock 1 and stock 2 as the covariance between stock 1 and stock 2 divided by the standard deviation of stock 1 and the standard deviation of stock 2. Because this is the case, we can rewrite the formula. So this is the same, and this is the same. But here it is changed. Here we have the standard deviation of both and the correlation coefficient all multiplied with each other. That's because of this relation. Well, where does this textbook formula come from? In nearly all textbooks, it just falls from the sky and no one knows where it comes from. I just want to show where it comes from, so for a better understanding, that's important, I guess. So, the variance of the portfolio can be defined the same way as we define the variance of a stock, by its value or by its return, or the variance of its return, of course. And it's a time series calculus, so I divide by time here, but nevertheless it's the standard variance formula, and I add up the days 1 to t, and of course it's the return of the portfolio on day t minus the average return of the portfolio. And all that, of course, squared. So this is the calculation of the portfolio variance. Well, but of course we don't have this. We want to have it in relation to the individual risk of the stock. So we could simply do the following, since we know that the portfolio returns are given by the weight of share 1 times the return of share 1 plus all others plus the weight of share n times the return of share n, we can simply introduce this return formula in here. And I would like to demonstrate exactly this idea. You can do it with as many stocks as you like, but of course calculation becomes more complicated then, so I do it with 2 stocks. So I divide again. I just now simplify my writing. I just sum across all t. And now we have a large bracket and a smaller bracket. And the weight of share 1 times the return of share 1 on day t plus the weight of share 2 times the return of share 2 on day t. So here we have this part, the return of the portfolio on day t, because it's just a weighted portfolio. And now we have to subtract the average returns. So the average returns are given by the weight of share 1 times R1. We can also denote it with a line on top, but it's not depending on time. It's just the average here. Plus the weight of 2 R2, small bracket, larger bracket, and squared. There we are. Now, of course, we can get rid of the smaller brackets and we can rearrange those 4 parts inside the large brackets. Let us just do that. I still need large brackets, of course. And now we have W1 R1 T minus W1 R1. So I take this, put it here, I take this, put it here, plus W2 R2T minus W2 R2. And I close the bracket and I square it. So this one is here and that one goes over there. Why is this one with the minus? Because we have the minus in front of the bracket. Okay, so seemingly we now have here and here something that is very similar to the variance calculation of a single stock. Okay, so we can use this, but now we have to apply the dynamic formula. I just clean up the screen a little and then we're going to do that. Alright, I just write down apply dynamic formula. Binomic. So that's pretty easy. We stick with 1 divided by t and the sum across all t. And now, of course, we have the first part, we have the second part. So typical use of the binomic formula. How do we do that? By W1 R1 T minus W1 R1 squared. So this is the first part of the binomic formula. Then we have the second part that is typically 2 times W1 R1T minus W1 R1 times W2 R2T minus W2 R2. And of course the last part then is W2 R2T minus W2 R2 and squared. Beautiful. And now I just remove the last formula here because I need a little space. I'm now going to distribute the 1 divided by t and the sum sign to all those individual parts, to all those 3 individual parts. So we have 1 divided by t and the sum across all t and the first part of the formula. So W1 R1 t minus W1 R1 squared plus second part 1 divided by t sum across all t, and of course since it's the 2 part here we can take the 2 out of the bracket and put it just in front there, and now the rest is W1 R1 t minus W1 R1 W2 R2 t minus W2 R2. And the third part of the formula now is again 1 divided by t, sum sign across all t, and W2 R2t minus W2, oh no, it's not a W, it's an omega. Nevertheless, you know what I mean, the weight, R2 and squared. So seemingly, this is some kind of weighted variance. This is some kind of weighted variance. And this is some kind of weighted covariance. Of course, we can also take those omega, those weights, out of the bracket. So they become, because it's squared here, they become W or omega squared. And since there are only factors in this, factors, coefficients, we can also pull them out. So the whole calculation reduces to, and that's very beautiful, W1 squared, and then the whole formula without the weight. So it's simply sigma 1 squared plus, I just take the last part first, so W2 squared sigma 2 squared plus 2 times weight 1, weight 2, and the covariance. And that's exactly the same formula that we have here. Well, in this formula, I just take the text marker or the highlighter. In this formula, we see that here the covariance, or here the correlation coefficient, plays a certain role. So the correlation between those two stocks plays a very, very important role. And I would like to demonstrate the role of this correlation in Microsoft Excel. I just switch to Microsoft Excel and demonstrate what I mean. Okay, I just opened Microsoft Excel and I built a little model where we can see how this formula works. So this formula in action. It's still a 2-asset portfolio, and what do we see here? I applied the typical framework, so color coding and so on and so forth for financial models, of course. And here we see some settings, and we can set the expected return of asset 1. So this asset number 1 has an expected return of, what is it here? 10%. 10%, of course. And we have a volatility of 0.2, so 20%. Here on the right hand side, we see the typical chart that is used. So we have the portfolio risk on the x-axis, the portfolio risk on the x-axis, and the portfolio return on the epsilon axis. And well, where do we find this asset? We find this asset here in the very top, because it has a volatility of 0.2 and a return of 0.1. Exactly this point is equal to that asset. And we can do that for a second asset in this line here. So this asset has an expected return of 5% and a lower volatility of just 8% or 0.08. So exactly this point is the other one. Now let us just assume here the correlation coefficient can be inserted or inputted, and then down here we see a whole lot of different portfolios calculated. So the first line is a portfolio that consists only of asset 2 because the asset weight is 1, for asset number 2, and for asset number 1 the portfolio weight is 0. And then in small steps this changes until at the end we see that the whole portfolio consists of asset 1. And then the usual formulas are taken into account. So here we see the portfolio return, and here we see the portfolio risk. So this is the formula we're talking about. We just took the square root to have the volatility here, because the volatility is entered for the single assets, and of course we need the volatility, so the square root of the variance. Well, and this data now makes up this curve. So this curve reflects different portfolio combinations between those two assets. So this portfolio here consists only of asset 1. And this portfolio here consists only of asset 2. And in between we see all the mixtures. So probably here we are somewhere in the middle. This is a 50-50 portfolio, mixed out of 50% asset 1 and out of 50% asset 2. So here we come closer to asset 2, and here we come closer to asset 1. And now the correlation coefficient plays a crucial role here. If those two assets were perfectly correlated, so they have a correlation coefficient of 1, we see a linear relationship, since it does not make any difference if we invest in 1 or 2. Of course, the one has less risk than the other, but if asset number 1 goes down, the other one is going down too. And if asset number 1 is going up, the other one is going up too. So the portfolio risk then is just a mixture, a linear mixture between those two assets. I'm now going to reduce the correlation. So I'm now going to reduce it to 0.5. They are still positively correlated, but we see that the curve gets a certain curvature. I go down further to a correlation of 0, and now we see something. Now we see that the curve has this belly-like curvature, and we see that there is a portfolio of the two assets, mixed out of the two assets, that has a higher return and a lower risk than asset number 2. So it is definitely worthwhile thinking about mixing, because the tip of this curve reflects a dominant strategy. Dominant in sense of it has at the same risk a higher return, or at the same return a lower risk. In this case it has both. It has a higher return and a lower risk. So it is definitely dominant towards an investment in asset 2. Okay, I'm now going to reduce it even more, and we see that this diversification effect, and this is diversification, even gets stronger. Of course, if we have a negative correlation, the one share is typically going up, the other one is typically going down, both assets might hedge each other. So if the one is going down and the other one is going up, fine, we don't lose money, so we can hedge against each other. And that ends with a correlation coefficient of -1 in a perfect hedge, because we have a safe, a risk-free invested if we find the combination between those two assets that is where those two assets extinguish each other's losses. So if the one is going up, the other one is going down. If we find a certain ratio between those two assets, we can have a risk-free portfolio here. But of course, this is rather theoretically, because we won't find any two acids that are perfectly negatively correlated. Usually, very much often, we see slight negative or slight positive correlations, but we still have the diversification effect reflected in the curvature of this portfolio. Okay, and now I would like to show how to transform this textbook formula into matrix calculus. And I would like to start with disentangling this formula into two vectors, or one vector and a matrix. And I would like to show how this works out for the two-asset portfolio, and then we generalize and see what happens in the multi-asset portfolio. So here we have the portfolio risk in terms of a variance. And this variance is now, since I just look at this formula, this variance is given by a vector of weight 1 and weight 2 times the covariance matrix and again multiplied by the same vector. Okay, of course, this vector is transposed, right? So I can write it like this, assuming that this is a bit bold. Can we do it like this? This is bold and this is bold, of course. Oh, ugly. Then it's matrix writing, right? We can test this. Let us test this. So of course I will need some like this. And to just give, so I'll take the left part now, omega 1 and omega 2, and here I put the matrix sigma 1 squared, sigma 1 2, sigma 1 2, and sigma 2 squared. Well, now I have to multiply omega 1 or weight 1 times the variance, so plus omega 2 times the covariance. And now the second part, omega 1 times the covariance and omega 2 times the variance. And this is still a vector. And now I can multiply this vector. I can multiply this vector again. By this vector. So I have to multiply this part times W1. That will be W1 squared sigma 1 squared plus W1 W2 sigma 1 and 2. So this times this is this. And now plus, I have to write it underneath, I'm sorry. So omega 1, W1 there is an error. This is 2, 1, omega 2, sigma 1 and 2 plus W2 squared sigma 2 squared. And now we see this part again, which is this part, and we see this part again, which is this part, and we see 2 times this. So we have 2 times this. So wonderful. Obviously our textbook formula works into matrix calculus too. Can we now expand this idea to more than 2 assets? Of course, we just need to enlarge our weights and our matrix, that's all. So generally speaking, we can now write down sigma portfolio is weight 1, weight 2, weight n, a huge matrix, sigma 1, so the covariance of a share with its own is its variance, of course, sigma 1, 2, sigma 1 n sigma n 1 sigma n 2 sigma n n. So this is our covariance matrix, and of course we have the weights again. And we have a general formula for what we want to calculate. Again, in matrix writing, sigma p square is then W. I try to make it fat again. Transposed the covariance matrix times the vector of weights again. And mathematically, this is called a quadratic form. Wonderful. Of course, we don't need necessarily to write it in matrix form. We can also stay in some sign form. If we like, we can also write it sigma p or sigma squared p of the sum across all shares with their weights and their returns. And that is, we need 2 sum signs now. A sum on I to n, and a sum j is 1 to n. And now we need the weights, weight I and weight j, and we need the covariances, I and j. So this is more or less the sum across the covariance matrix. So one of the sums sums the columns and one of the sums the rows. And this is the covariance matrix that is weighted with the weights. Last but not least, I would like to show how these calculations can be performed in Microsoft Excel. I already prepared the whole model, but I would like to guide through that model. So in the rear part of the model, I store all the raw data because it's exhaustive data and no one really wants to see that anymore later on. I stored it. So I have a 3-asset portfolio here that consists of Adidas, ADS, Deutsche Bank, DBK, and Vonovia, VNA. And I just downloaded all the stock price data using Yahoo Finance historical prices. So I have some kind of raw part here. Then I'm aggregating, because I just need the adjusted close, I'm aggregating that to price data. Of course it's blue because it's linked data, and I aggregated this data using the typical VLOOKUP formula, or in German it's S-Verweis, VLOOKUP, and it looks up simply the date, and so I get this data aggregated. Adjusted close as of Adidas, Deutsche Bank, and Vonovia. Then I perform calculations on it, of course. I calculate the log returns. Here are the log returns, of course color-coded as calculations. And we see that here we calculate the log differences. So price of today minus price of yesterday. In the very first line, the very first line must be blank. I just wrote intentionally left blank so that a reader of my model understands, okay, this is intentionally blank because we can't calculate a log return there. I've put in all the calculations, all the other calculations now onto one sheet. For practical use, I would recommend to put the covariance matrix on a sheet on its own, because it can easily grow very big, and we want to use the model as flexible as possible, so we need a bigger one. But here it is fine, so that we have it at one side. So here the covariance matrix and the correlation matrix are calculated. The command for the covariance matrix is covariance P. P means that the covariance is calculated based on the population. There's also a command covariance as. S stands for sample. Here we apply P. And now I did a little trick. This covariance, as you just see on the screen, the covariance command wants to have two arrays. Two arrays, so just like two vectors, of course, from the log return sheet. But since I don't want to rewrite the formula over and over again, I indexed it. So my covariance, I just go to another covariance. I just go like here. I always apply the same command. It's always this index, and the index is 2 times. So 1 times index command and another time index command. The index just is also a kind of lookup command that looks up a range or an array. And the index here looks up in the log return sheet, in that area where all the log returns are, and it takes the first column there. No, I'm sorry, the second one. Look here, it grabs the 2 and it grabs the 3 for the second index. So the second column and the third column are both given to the command covariance. And it is multiplied by 250 to annualize all that. We don't need to annualize if we do the same with the correl command, which just gives back the correlation coefficient. That one is standardized on its own, and we don't need to annualize anything there. Well, a nice feature, of course, of the covariance matrix is that on the main diagonal we see the variance, the individual variances of Adidas, Deutsche Bank and Vonovia. So the stock risk can be simply taken from there. Here we see those 0.16. Here we see 0.32, and here we see 0.08 given there. Then we can annualize the variance by just multiplying by 250. So here we have the annualized variance. We can calculate the standard deviation, and we can annualize the standard deviation. But stock risk is not that important for our portfolio view because we have the covariance matrix and there's all the information in. Then I calculated average daily stock returns here as an average of log returns. And of course the annualized average stock returns using the exponential formula. So it's a compounding formula that I apply here. And of course I give the whole thing the portfolio weights, and here I weigh the portfolio equally. So what I calculate here is an equally weighted portfolio. I can change the portfolio weight, of course, 0.5. Here you see a check so that the portfolio weight always needs to add up to 1. So this is not yet given, so I get a red flag here. But let's stick with the equally weighted. And here's a portfolio return. So I just multiply those two vectors, and vector multiplication is done with the mmult command here in Excel. So I have to give two arrays again, and they will be multiplied just by calculating the cross product. So of course I have to transpose one of them. I took the first one and multiplied by the other. Please keep in mind that this is a matrix formula, so if you enter this formula, you don't need to enter, but you need to enter control uppercase, control uppercase, and enter. So that's the trick for matrix formula. The same is true for portfolio risk. I apply the mmult twice here. On the inner side, I just multiply the weight vector with the covariance matrix. And then I multiply all that again with the transposed weight. Why do I transpose here and not here? Because these are vectors that are already laying. They are horizontal, and accordingly I have to transpose the other vector. Now I get a value error, but I can go in here, control uppercase and enter, and there's the result again. So here's my portfolio risk. I hope this video helped you. Thank you for listening and see you in the next video.